Hi folks, welcome back to Physics with Captain Rod. I make this video to provide the first example here of how to use, how to write equations of motion for a object or particle. So what we're looking at here, I imagine we've got this car and at t equals 0, it has an initial velocity that I'm going to call v sub o to the right. And imagine that the person is stepping on the gas, in which case the car, this velocity would be increasing, so we'd have an acceleration also to the right. This distance here would be what I would call the initial position of the car with respect to this coordinate system. This would be, some positive number. I'll just put some number here in this problem. And what we're going to do now is talk about how to derive equations of motion for the velocity of the car and the position of the car. Now, I've got these graphs kind of left over from my previous video here. What we're going to do is we're going to look at one of the standard or very common cases in physics, the case of constant acceleration. So this acceleration here, whether it be 3 or 4 meters per second squared, whatever the numerical value, that's not important. We're just going to call it a for acceleration, but we're going to assume it's not changing. That's a pretty common case in lots of different physics problems. So I'm going to go back and modify my graph here some. In fact, I'm probably going to modify all of these. All right, so if the acceleration is in fact to the right and constant, then this graph now would look something like this. This is, we'll just call this some time t here. And then the delta v would be given by this area here. So I'm going to go ahead and write this out. Your change in velocity is going to equal this area. Now, this distance on the graph is what we're calling a, the acceleration of the car. This distance on the graph is what we're calling t. So the product of the two is just a times t. Now, delta anything, remember, is v final minus v initial. So we've got, I'm just going to call it v minus v initial. So this v is our v final, or our time-dependent v. And that's going to equal acceleration times time. And then you just solve this for v. And we get v initial plus at. Now, presumably v initial some number, the acceleration some number, and what we have is a linear function now. So if I were to plot this over here, get rid of this here. This might look something like this, out to some time t. So here's a very important relationship to understand. So this distance is what we're calling t. I'll do this one in, well, let's use this light blue here. This distance right here is described by this function that we just derived. All right. Next one. Now to get our position function. So our delta x, remember, is given by the area under this velocity graph. Now that's going to be this area right here. Now, some very important things to realize. This distance, I left it blue there, is the initial velocity of the car. And this distance here is described by, oops, let me get rid of this function. So when we calculate the area, we're going to be calculating the area of this rectangle. I'm sorry, that's not a rectangle, that's a trapezoid. So if you're not familiar with finding the area of a trapezoid, again, I got videos on finding the area of a trapezoid, just go review them, but it's basically the left plus right divided by 2 times the width. So in our example here, the left is what we're calling v sub o. The right is described by this function, v sub o plus acceleration times time. I'm going to put that in parentheses because it's left plus right divided by 2. And then times the width, t. And it's pretty easy to go through and distribute this and simplify. This ends up equaling v initial times t plus 1/2 at squared. Now, delta anything is always final minus initial. So this delta x can be written x final, I'm just going to write that as x, minus x initial, and then equals the rest of this. And if we just put the x initial on the right, we get the following. And there is our function for the position of the car. Now, the right ways to learn this and the wrong ways. Nobody on the planet should spend any time really memorizing these formulas. That's not what I'm going through the video here with you for. The point of this is how these equations are derived. Now, another thing I'd like to point out, I've done this in an algebraic sense here. These can be derived using methods of calculus. I'm going to save that for another video. This video is good regardless of the physics class you're in, whether it's a calculus-based video or not. The important thing here, the basis of the derivation going from acceleration to velocity to position, is that your change in v is equal to the area under that acceleration curve. And your change in x is equal to the area under that velocity curve. That's the fact that allows us to take an acceleration and find from it a velocity graph and then, or a velocity function, and then a position function. Now, this was done kind of generically using variables. In my physics classes, we usually start out by doing these kind of numerically to begin with. For example, the area under this trapezoid, if this car was starting at 4 meters per second and this was 12 meters per second for 6 seconds, this area is a very simple calculation to find the delta x. And we do this all the time at the beginning of a physics class. Well, the only difference between that and this work is really the names. This blue line here, rather than it being a number, we are attaching a function to it. And what that does for us is it gives us results and equations that are good for all time. Anyway, this is just meant to be an introductory video in deriving equations of motion, non-calculus methods. So I hope that this gives you a little bit of a sense of how to do that. Have a great day.